This video will be covering DIT or diffusion models with transformers. For all our past diffusion videos, we have been working with a UNet architecture, where we had a series of encoder blocks, mid block, and a series of up blocks, with skip connections between encoder and decoder blocks of same spatial resolution. The authors of DIT replaced this UNet architecture with a transformer, and similar to latent diffusion models, work on latent images rather than image in pixel space. For this, the authors based their architecture on Vision Transformer or VIT. The way we'll go about with this video is first to do a quick review of VIT. If you aren't familiar with VIT, then I've already covered it in detail in previous videos, so I would suggest to watch those first. Here we'll only refresh some aspects of it. Then we'll see the changes the authors make to get to DIT, and finally look at its implementation and results. So in VIT, we had a sequence of transformer encoder layers. These layers work with sequence of visual tokens of the image. And these visual tokens are basically representations of patches of height and width 16. Along with these visual tokens, we also add a learnable representation for CLS token. For training VIT on image classification task, this CLS token's last layer's representation was used to get us the classification scores using a FC layer. To transform the input image into a sequence of patch tokens, VIT has a patch embedding block, and the input image is actually fed to this block. Let's look inside the patch embedding block and a single transformer layer of VIT. For patch embedding block, the goal is to convert the image into a sequence of visual tokens. For this, we divide the image into patches of width PW and height PH. And say for this image, we happen to have these 4 patches. Each of these patches have number of channels times height times width pixel values, which are then converted to a d-dimensional representation, which is the hidden dimension at which the transformer layer is going to be working. Rather than using FC layer, we could also do this with convolutions, with patch height and width deciding the kernel sizes and strides, and D being the output channels. In order to fuse into this representation some knowledge about the order of patch tokens, we use position embedding, which for VIT was representations for absolute positions of these patches. So using a learnable embedding layer, we got these position representations, and they were added to the existing patch representations to get the tokens that will ultimately be fed to the transformer layers. For the classification task, VIT authors also append the CLS tokens representation, with its position being represented as 0. This is all about patch embedding block. Now on to the transformer layers. For the transformer layers in VIT, we have a layer norm, followed by self-attention with a residual connection, and then another layer norm, followed by MLP, which is 2 linear layers with activation, and then again a residual connection. Then these transformer layers are stacked one after another to give us our VIT model. Now we are going to start with changes from VIT to get to DIT. For diffusion transformers, since we are interested in generating images, say of 256 x 256 resolution for now, then we won't be needing these classification layers, and the entire transformer would be expected to take as input a noisy image and generate as output either the denoised image or noise prediction. Furthermore, rather than working in pixel space, the authors of DIT work in the latent space by encoding the images using a pre-trained autoencoder, specifically the same VAE that was used by authors of latent diffusion models, with a downscale factor of 8. So the input images will actually be noisy latent images of 32 cross 32 with 4 channels, as that is the configuration of VAE used. And the output will also be a latent space image or noise prediction. And after the last transformer layer, we would get the denoised image prediction and feed it to the pre-trained decoder of VAE to get our generated image in pixel space. Now let's look at the changes in patch embedding block. If we would be doing the exact VIT implementation, then we would have something like this. Take the sequence of patches, project them to transformer dimension via linear layer, and then add learnable absolute position embeddings as position representation. For DIT, for converting grid of patches to sequence of patch representation, we would do the same, projection via linear layer. It's just that channels will now be whatever is the Z channels or latent dimension of our autoencoder. The only thing that is different from VIT to DIT is regarding position embeddings. Instead of using 1D learnable position embeddings, the authors use 2D sinusoidal position embeddings. So we consider the input as a grid of patches. And now each patch, instead of being represented by one position, is represented by two positions. Position across X and Y axis. Sinusoidal embeddings for both are used to get d by 2 dimensional representation for positions across both these dimensions. So here for our example case, the first patch will have d by 2 dimensional representation for 0 and 0. For second, it will be representations of 0 and 1. Third will be 1 and 0. And the last one will be 1 and 1. Then both these representations are concatenated to finally get a d-dimensional position representation for these grid of patches. As a side note, this is kind of something that the authors of VIT also tried, where instead of using 1D learnable position embeddings, they used 2D learnable position embeddings. But they did not find significant differences between 1D and 2D with regards to performance. For diffusion transformers, the authors don't provide any details on any kind of experiments they did regarding position embeddings, other than the fact that sinusoidal embeddings are being used. But when you look into their official implementation, there it's 2D grid embeddings. The second change is on the final layer side. What we desire from the output of transformer is ultimately an image. But as of now, it's going to return a sequence of d-dimensional tokens. The authors of DIT add an unpatchify block, which has a layer norm and MLP, and it takes in the d-dimensional tokens as input and transforms each of them to a dimension of patch height times width times input channels, which would be Z channels. These can then be transformed to latent patches and then combined to get this latent image. During training, this is all we need. But during inference, we need to generate the image in pixel space. So we would additionally call our pre-trained decoder of VAE to convert this unpatchified latent image to image in pixel space. Now for diffusion, we need to pass time step information as well to give the model some sense of the extent of noise present, and also conditioning information like class or text if present. In our unit models that we have been working with, the way we have been handling it so far is that the time step information is converted to time embedding using sinusoidal embeddings, and we would pass that to couple of FC layers to get the time step representation, which is then passed to all ResNet blocks where it's added between the two convolution layers. For text conditioning, we took the text representation from a text encoder and had all the blocks attend to this representation through cross-attention layers. And finally, for class conditioning, we got the class representation using an embedding layer and just added to the time step representation prior to passing it to the ResNet blocks. The authors of DIT try out 4 different variants for passing the time step and conditioning information to the model. But for conditioning, the authors only experiment on class conditioning. All the 4 variants use the same mechanism to convert the class and time step information to a d-dimensional representation, so the hidden size of transformer. So let's see that first. The time step t is first converted to a representation using an embedding layer, and similar to previous diffusion architectures that we have seen, this is a sinusoidal embedding layer. This time embedding then goes through 2 linear layers to give us a d-dimensional time step representation. So this particular conversion from time step to time step representation is exactly same as previous unit architectures, except there we ultimately added these two ResNet blocks. To get a class representation, the authors use a learnable embedding layer, which gives us the d-dimensional representation for each class. Now let's look at the 4 variants. So this is our DIT block, and up till now it's exactly same as VIT transformer block, which receives the sequence of tokens from previous layer or patch embedding block. The first variant is called in-context conditioning. In this, the authors add the class and time step representation as 2 additional tokens to the input sequence. All the transformer layers now operate on this new sequence of tokens. And obviously before the unpatchify block, after the last transformer layers, we would get rid of the first 2 tokens and work only with the patch tokens. The second variant is cross attention, where now we add a cross attention layer with a layer norm prior to it between the self attention and MLP block. The time step and class representations are now concatenated as a sequence of 2 tokens. And this cross attention layer that we just added is actually going to attend to this 2 token sequence of class and text representation. The third variant of DIT block is adaptive layer norm. Very similar in spirit to what we do in StyleGAN, if you guys are familiar with it. If not, it's fine. I think soon I'll be doing a video on that anyways. So here the time step and class representation are added, and this now goes through a MLP to give us 4D values. These 4D values are used as dimension-wise affine parameters, so scale and shift parameters, after the layer norm. Now layer norm by default learns these affine parameters. But in this variant, we disable that and learn to predict these affine parameters from the conditioning input of time and class. The fourth and final variant is very similar to the previous one and is called adaptive layer norm 0 block. In this, from the MLP, we now predict additional 2D values, so a total of 6D values. These are used to predict the scale by which we'll multiply the output of both the MLP and attention block prior to the residual connection. The weights for this MLP is initialized such that the scale predictions are 0 initially, which means the entire DIT block kind of just acts as an identity function at the start, similar to identity mappings in residual network, to ensure better training of the entire network. For their experiments, the authors built 4 different configurations of the model, scaling from the smallest DIT model, which is a 12-layer transformer with a hidden size of 384, to the largest DIT model with 28 layers and a hidden dimension of 1152. Apart from the increase of scale by increasing the transformer depth or width, the authors also explore additional dimensionality of scale, that is the number of input tokens. For that, given the latent image size of 32 x 32, the authors experiment with 3 different patch sizes. Patch size of 8 x 8, giving us a sequence of 16 tokens. Patch size of 4 x 4, so a sequence of 64 tokens. And finally patch size of 2 x 2, giving us a sequence of 256 tokens. To compare different conditioning design choices, the authors train the DiT XL model with patch size of 2, with all these 4 block designs. And to compare the performance, they use FID 50K metric. So what's this FID? Well, this is a metric commonly used to compare generated image quality and was proposed in one of the earlier GAN papers. The idea here is that we have a distribution of real-world images present in our training as well as testing dataset, and a distribution of fake images generated by our generative model. To compare the quality of different generative models, we can use the distance between these two distributions, and the model that generates a distribution of images that are closer to the distribution of real-world images is a better one according to this metric. The way we compute this metric is we feed a sample of real-world images to a pre-trained model, which is usually Inception v3 pre-trained on ImageNet. We get the output of the model after feeding these images, and here the output used is activations prior to the last classification FC layer of the model. From these output features for all the real-world images, we compute the mean and variance of real-world distribution of features. Similarly, feed the distribution of generated images to the model and get the mean and variance of output activations for these generated images. Then we use this distance metric between two Gaussians to get the FID. So lower the FID, the better, as the distribution of generated images is closer to the distribution of real images. And 50K just represents the number of image samples used to compute this metric. Now back to the result of performance of different conditioning strategies. The authors find that in-context conditioning, where we just added the text and condition as two additional tokens, perform the worst. Cross-attention block is very similar to adaptive layer norm, and the adaptive layer norm 0 block ends up achieving the best FID. Do keep in mind that this is specific to class conditioning. The same result might not be necessarily true for something like text conditioning, where even though you could do adaptive layer norm with pooled text token embeddings, but I'm guessing cross-attention should perform better. Like here is an example of a later paper which trains DiT for text-to-image generation, and it also uses cross-attention for text conditioning. With the adaptive layer norm 0 block design chosen as the DiT block for class conditioning, the authors then compare across different configurations to visualize the impact of both the dimensions of scale, transformer size and patch size. Not surprisingly, as you increase layers and the hidden dimension size of transformer, the performance becomes better and better across all patch sizes of 8, 4 as well as 2. Keeping the transformer configuration fixed, the smaller patch sizes, which have the largest number of input tokens, perform the best. And as we increase the patch sizes, keeping the remaining configurations of transformer fixed, we see worse FIDs. And this is true across all the sized models. Looking deeper, comparing different patch size variations for the same sized model, say DiT XL, if you calculate, you will see that the parameter counts of these models aren't much different from each other. In fact, the parameters for patch size 2 variant is actually slightly lesser than that of size 4, which is lesser than that of size 8. This is because of the patch embedding block and the unpatchify block parameters, as they increase as one increases the patch size. But still the FID of patch size 2 is better than the others. Now while the parameters of patch size 2 variant is not larger than that of 4 or 8, but when we look at flops, the flops are considerably increasing as we go from XL8 to XL4 because of XL4 working with larger number of sequence tokens, and same when we move from XL4 to XL2. This indicates that it's scaling flops that actually matter for performance, The authors then compare model performance for all configurations with model G-flops and find strong correlation between model flops and performance as measured by FID. Whereas you keep increasing flops, FID gets better and better, suggesting that adding more and more flops or compute is a key component of getting improved performance with DiT. The largest model that the authors train in terms of flops is DiT XL with a patch size of 2, and it generates images with really high quality, and in fact ends up getting an FID that's even lower than latent diffusion models. And this is while having an architecture complexity as measured by G-flops very close to LDM. We will now go through an implementation of DiT. But before that, let's just summarize all aspects we covered to get to DiT from VIT and take a look at all the different parts of DiT model with adaptive layer norm 0 block. For DiT, we start with VIT architecture and get rid of classification layers. Work in latent space rather than pixel space. Add time step and class condition to get conditioning representation. Convert each VIT block to adaptive layer norm 0 block. And finally add unpatchify block at the end of transformer layers. Like our previous diffusion model implementations, we'll be training DiT on CelebHQ with similar kind of config that we have been working with. Just that now model params will actually be DiT configuration parameters. So this is the config, and we are training DiT B model with patch size 2 here. The bunch of parameters that we are concerned with are patch size, number of layers in our model, its hidden dimension, the attention parameters, and time embedding dimension. Now since this config is for training on latent images, we also have autoencoder parameters here. To start with understanding implementation, let's get into patch embedding block, which we saw is just going to have a linear layer to convert the input image from a grid of patches to sequence of tokens, and also be responsible for baking in positional information into these tokens. All patch embedding block module has is one linear layer. This linear layer is going to have input dimension as channels in input image. So this would be Z channels, which is 4, times patch height times patch width, and the output dimension will be hidden size of transformer, which is 768 for DiT-B. This initialization I have is just copied from the official repo. In papers, the author mentions specific initialization for the adaptive layer norms MLP and the final MLP, which we'll look at later. But for all the other linear layers in the code, this is the initialization that they use. In the forward method, we first transform the input image into a grid of patches, and then from the grid of patches to a sequence of patch tokens, each token of dimension patch height times width times channels. This rearrange function from enops takes care of that transformation for us, converting batch cross channels cross h cross w, where h is nothing but number of patches along height times patch height, and same for width, to batch size cross number of patches cross patch dimension. Then using the linear layer, we go from patch dimension to transformer dimension for each of these tokens. Now on to the second responsibility of patch embedding block, which is adding positional information. This method takes care of getting the 2D sinusoidal position embeddings for the patch tokens. This gets as input the grid size after patchifying. So assuming input of 32 cross 32 and a hypothetical patch size of 16, grid sizes along both height and width will be 32 by 16, so 2. which means this method will return the 2D position embeddings for the 2x2 grid in that case. We first get the indexes of positions along both dimensions, and then create a grid of these indexes, giving us the x and y index positions for each of those patches. Then from the flattened x and y positions for all patches, we get a d by 2 dimensional sinusoidal representation for both x and y positions. Concatenating them gives us a position representation of dimension d for each of the patch tokens. And finally, patch embedding block adds this positional information to the patch tokens and returns these tokens. Now let's move to the individual transformer layer. We'll only work with the adaptive layer norm 0 block variant, as that is the one that's ultimately used in DiT. And for this, we first have the layer norm for attention block. And for all layer norms, because this is the adaptive layer norm variant, we'll disable the layer norm from using its affine parameters. This argument does exactly that. Without this, Pytorch would actually go ahead and also include a weight and bias parameter. But instead, we want to regress these from the time step and conditioning input. Hence, we disable these default learnable parameters for the layer norm module. Then the attention block, and this is exactly same as VIT attention block, which I have discussed in detail in my VIT videos. But let's just do a quick pass over it. This is going to have a linear layer to get the QKV representation for each of the tokens, and another linear layer for output projection post the scale dot product attention. In the forward method, we get the QKV representations for all the tokens in the sequence, compute attention weights, and then after using these weights to get the value representations, we use the output projection layer to get back to the transformer hidden size dimension. Just like attention, we also have a layer norm for MLP. And then the MLP block. With the default hidden dimension of this MLP block being 4 times the transformer dimension d. Now for each block or layer, we use the conditioning input to predict 6 dimension-wise scale and shift parameters. These would be the scale and shift parameters for the layer norm of attention, scale and shift for layer norm of MLP, and scale for output of both of these prior to the residual connection. This linear layer computes all these 6 sets of values from the conditioning input that each block receives. DiT authors initialize this layer such that the alphas are all 0 at initialization, making the entire DiT block as an identity block. So we initialize this MLP weight and bias to be all 0 for that. Note that this would also zero out the layer norm scale parameters at initialization. In the forward method, whatever is fed as conditioning input to the layer, we first use that and the adaptive norm MLP to get the 6 scale and shift dimension-wise values. Then we first have the layer norm of attention block. And now instead of multiplying with scale and adding the corresponding shift, we multiply it with 1 plus scale. And because the scale output will be 0 at initialization, doing this effectively makes the layer norm scale at initialization to be 1. So at the start, this layer norm scale and shift parameters won't be modifying the layer norm output at all. Then we get the attention output and multiply it with post attention scale parameter and add it to the output. And as we saw, the post attention scale parameter at initialization will be 0, making this entire operation equal to identity at start. Same thing we do for MLP block, layer norm, scale and shift, then MLP, and then post MLP scale, and finally return output after the residual connection. And again, because both these post attention and post MLP scale parameters, which were alpha 1 and alpha 2, are initially 0, this makes the entire DiT block just an identity block at start. Now let's look at our main DiT model class, which is going to make use of these transformer layers and patch embedding block. During initialization, after getting all the parameters from config, we instantiate our patch embedding block. The time step information needs to be converted into a representation with same size as hidden size of transformer. So these linear layers take care of exactly that. And they are going to receive the sinusoidal time embeddings as input. These are all our transformer layers, so instances of the class that we just saw. These three are the final layers, which we can refer to as unpatchify block. So we have a layer norm, and when the DiT blocks are adaptive layer norm variant, the final layer norm also has the same scale and shift parameter prediction from conditioning input, which is why again we disable the default learnable affine parameters of layer norm. This is the linear layer for predicting the scale and shift parameters, and here we just need two sets of per dimension value, which will just be the dimension wise scale and shift values. Lastly, the output linear layer, which is going to convert each patch token from hidden dimension of transformer to an output dimension of patch height times patch width times channels, which will be the Z channels of our autoencoder. And we have the same layer norm initialization of 0 scale and shift at start. Additionally, the authors initialize the weights of final linear layer to also be all zeros. In the forward method, we call the patch embedding block, convert time step to its sinusoidal embedding representation using this function, which we have also used in previous videos with unit architecture. And then use the time step FC layers to get a time step representation of same size as the hidden size of transformer. Then we go through the transformer layers one after the other. Then use the layer norm MLP to get the scale and shift values for this layer norm, and do the scale and shift accordingly. Then call the final linear layer to get the output of shape channels times patch height times patch width for each patch tokens. At last, this rearrange is kind of doing the opposite of what we did inside the patch embedding block. This will transform the sequence of patches, each patch of dimension channel times patch height times patch width, to a grid of patches. And that's it as far as DiT model code is concerned. We'll be training DiT to predict the noise that was added in the image, similar to previous diffusion videos. So this returned output would be that noise prediction. The training and inference portions are exactly same as previous diffusion videos. No change at all. For training on latent images, we'll additionally have VAE to encode the image or load saved latents if present. The exact training, sampling, and noise scheduler implementation is the one that we have already seen in DDPM and LDM videos, where the model is trained to predict the original noise that was added. And once it's trained, we sample starting from a random noise and go through the reverse process till we cover all time steps and get a prediction of original image. If you aren't familiar with the specific implementation of diffusion and noise scheduler, I talk about it in detail in my DDPM implementation video. So do check that if you want to have a better understanding of it. There is one difference between my current DIT implementation and the official one. For training, the authors actually learn the variance of reverse process as well, as proposed in this paper. But as of now, the code that I have only provides training using the same original DDPM strategy, where the variance is fixed. However, other than learning variance part, rest of the implementation is exactly same as official DIT implementation. So let's see the results of training this on CelebHQ. I found DIT to be better not just in terms of final output from the limited experiments that I did, but even time taken to start getting decent outputs. Like for CelebHQ, within a few epochs itself, I started getting a face-like generated image. And these are some results after training the model for about 200 epochs. All the code that we have seen, as well as the training and sampling code, I've pushed to the repo. So do try DIT on your datasets and see how it fares in comparison to LDM for your use case. And let me know in case you run into any issues with the code. That's about all for this DIT video. Thank you guys for watching these videos, and I shall see you in the next one.